And we're live.
Good morning, good afternoon, and good evening, wherever you are watching around the world. Welcome to SETI Live. This is an east and west coast of the US edition. My name is Simon Steele. I'm the Director of Education and Public Outreach at the SETI Institute, and I'm talking to Veselin Kostov, who is an astronomer, scientist at both the SETI Institute and also at NASA's Goddard Space Flight Center over in Maryland. And that's where you are at the moment, Veselin, isn't it?
Yeah, it is. Thanks for having me.
Yeah, so we are going to talk about Planet Patrol, which is an exciting new citizen science program based around data coming from the TESS spacecraft. Please, as we talk about this, do send us your questions. Do let us know where you're watching from, and we'll try and get to as many of your questions as possible. So I think maybe a good place to start, Veselin, is actually a lot of people would be familiar with TESS. Some people may not. So I wonder if you could say a little bit about the TESS mission to start with.
Sure. So TESS is the latest exoplanet spacecraft mission coming from NASA and from MIT. It's a telescope in space. It's basically a collector of light. It looks at the entire sky, and it measures the brightness of a very large number of stars across the entire sky using 4 different cameras. And the telescopes themselves are nothing crazy big. There, you can think of them like 10 centimeter lens. There are 4 telescopes. Yeah, there it is. Thank you, Simon.
Yeah.
So you can see the 4 cameras. These are the 4 things that look at the sky at slightly different angles. And TESS was designed to find transiting exoplanets around bright nearby stars, and to find a number of them that we would be able to measure the masses of.
Okay. And TESS is a follow-on from the Kepler mission, isn't it? Now, the Kepler mission is again was looking for transiting exoplanets, but the main difference in strategy there was Kepler was always pointing at the same point in the sky, looking at a very small area of sky over and over again, and actually picking up much fainter stars and much fainter planetary candidates, whereas TESS is doing the whole sky, the whole night sky in its orbit.
Yeah, exactly. There are differences in strategies and also differences in the corresponding design. As you mentioned, TESS was staring at a relatively small patch of the sky for about 4 consecutive years, continuously staring at that patch of the sky, whereas TESS is covering the entire sky, both the south and the north, in these sort of orange slices. It cuts the sky in orange slices every 30 or so days. So it's a trade-off between the number of stars that you want to observe and how well they want to measure their individual brightness.
Right. We've already got a lot of people tuning in, so I'd like to say welcome to viewers from Germany, Norway, Seattle, Montreal, Herndon, Virginia, Quebec, Portugal, Houston, Texas, Nottingham in the UK, and South Carolina. So welcome, everybody, to this SETI Live. Veselin, I'd like if you could say a little bit more about what TESS is doing and what Kepler did before, and the type of observations it is making to discover planets.
Sure. So both Kepler and TESS are basically photometers, meaning it's an instrument that measures the brightness of a star as a function of time. So to do that, as we both mentioned, Kepler was looking at about 200,000 stars for 4 consecutive years. So ballpark, you have 200,000 stars. You measure their brightness every 30 minutes, and you do this for 4 consecutive years, 4 continuous years. So you can imagine the amount of data that comes from that mission. The strategy of TESS is different. TESS is looking again at the entire sky, so you have tens of millions of stars across the entire sky. what you gain in the number of stars that you observe, you lose in the amount of time that you can observe them. So compared to the Kepler's 4-year continuous monitoring, TESS is looking at stars for anywhere between 30 days and about 360 days. It depends on where on the sky you are. And the TESS is a smaller telescope, 10 centimeters compared to the 1 meter mirror of Kepler. So you also, the two different missions have different sensitivities. And the goal of both is to detect transiting planets, transiting exoplanets orbiting distant stars. And we do this by measuring the brightness of the star for ideally as long as possible. And we try to see if there is a periodic decrease in the brightness of the star, which would indicate that something is blocking the line of sight between the observer and the star, ideally periodically, which is what usually planets do.
So you're looking for of course, you can't see the planet; it's too small. All you can see is a point of light, 1 pixel.
Exactly.
Essentially, and you're looking at how it stays at a steady brightness and then maybe dips a little bit, a couple of percent,
exactly,
barely noticeable. And that's a suggestion that there is something either happening with the star or something passing in front of the star.
Exactly, and we also need to believe that we also need to trust that Newton's laws of motion work as well as at the other edge of the galaxy as they work on the Earth. So you see something orbiting, you can analyze the system using basic physics, orbital motion of bodies. And ideally, what we want to see is what we see on your background. Unfortunately, that's not what we see. As you mentioned, we see a couple of flickering pixels on a small image.
That's right. We should point out that what's behind me, and I can't remember, it's one of the Kepler discoveries. I can't remember which one, 456 possibly, but this is not what you see through the telescope. All of these beautiful sort of artists' impressions are just based on scientific ideas, but we do not see these planets even. This is a variation in brightness of the star, and as you said, you need this alignment of us, of the TESS spacecraft, the star, and then the planet passing between us. There may well be lots of planets, but they could be orbiting at 90 degrees to that, and of course then you would never see them. So we've already got this sort of selection effect going on, haven't we?
Absolutely, and this is a very strong selection effect. Let's say for every planet that you see in transit, you don't see 100 planets that don't transit, just because the inclination of their orbit is such that we don't see them. Someone else somewhere else may see them, but we don't.
Which makes it very exciting, because if we, with all of the observatories have discovered 5,000 plus exoplanets, planets around other stars, and this is maybe, a few percent because of the orientation. That says how many planets there are out there, which is quite amazing. But there are other things that can cause a star to dim. There are sort of false alarms. What else? You look at a star, you see this slight dimming, and you think, yes, I've discovered a planet, but that's not necessarily the case, is it?
Exactly. Unfortunately, there are a very large number of things that can mimic a planet, mimic a transiting planet, but is not. What you're seeing could be due to systematic caused by the instrument itself. Something happened at that particular time, and the detector that did something funny, which looks like a transit, but it's not. Or it could be real astrophysical variability caused either by the star itself, for example, because there are spots on the star, so as the spots rotate, you see the spots coming in and out of view. Or there is something else on the background or on the foreground of the star that is also variable, which may mislead you into thinking that you're seeing a planet, but it has absolutely nothing to do with the planet. Or probably the predominant effect that can confuse you is an eclipsing binary. An eclipsing binary is basically a binary star. These are two stars that orbit around each other rather closely, and the orientation of their orbit is such that we see them blocking each other's light periodically. And basically for any signal that you see and you think is a transiting planet, there is an equal or even higher probability that that's actually what you're seeing is an eclipsing binary, which is interesting on its own. But you cannot live on it. So
it's more interesting if you're a stellar astronomer than a planetary astronomer.
Yes, exactly. I mean, eclipsing binaries are amazing. Don't get me wrong. It's just
And this, I suppose, is where Planet Patrol comes in, isn't it? Because what you have is a lot of potential exoplanet candidates that are appearing in this data. And there are algorithms that will allow you to sort of sort through this. But in the end, it's really the human brain, the human eye, that can pick out some of these false signals from these real signals. And that's where the scientists have enlisted the help of what we call citizen scientists, who are not employed professionally as astronomers, but have a fascination to get involved in these projects and potentially make these amazing discoveries. So I'm just going to run down the list because we have a lot of people signing in, and then we'll start talking about the planetary Planet Patrol itself. We got people listening in from Rio, from Australia, Denver, Simi Valley, I hope I pronounced that right, in California, Burnie, California, Finland, Romania, Saskatchewan, Denmark, Amherst, New York, Croatia, Missouri, and Washington. So that's quite amazing. And we just got somebody from Hong Kong who's joined us. I just want to say that we do have another live presentation coming up. So I'm just going to advertise this in the middle of, while we've got everybody's attention. Next Thursday at 2 p.m., we'll be having a SETI Live with Seth Shostak talking with Andrew Simeon, who is the director of the SETI program at the SETI Institute. And we'll advertise that on our website. So please do listen in on that. And that's on Thursday at 2. So that's this Thursday at 2, not next Thursday at 2. So thank you. Sorry to interrupt, Veselin. Let's go back to Planet Patrol. What was the inspiration for this project?
I think there were two main inspirations. One of them was practical, meaning that, so I have to go a step back. Planet Patrol is about vetting planet candidates from TESS. This means that we try to rule out all possible sources of false positives, just like we discussed, like eclipsing binaries or instrumental noise. So the main reason was practical because we have so many targets and stars to look at that, our group is really a handful of people, mostly me. Ideally, we want to help the algorithms and the computers by inspecting their results. Computers are great and they're doing a fantastic job most of the time, but in some cases they get confused by one type of noise or another type of noise. And where they fail, the human eye is really good at catching these because we can easily find the patterns where computers struggle. And people started doing machine learning just because it's similar to human learning, what one of my colleagues says on eye learning, like an eye learning. We learn by looking at things. So one of the reasons was practical. We don't have the capacity to inspect all the possible different candidates. The second main reason was that current and previous citizen science efforts on Zooniverse that are tailored for exoplanets have been fantastically productive and an amazing resource and an amazing source of producing science and engaging the community. So we decided to combine these two aspects and put forward this project.
Right. And we'll put up the links to Zooniverse, which is the umbrella project that has a lot of citizen science programs, not just astronomy, but biology, physics, and so on. And they are really worth looking at. But I think it's probably time to dive into Planet Patrol and just see what it looks like. And as I say, with the links to all of these will be put up on the feed, and on our website, so you don't need to write these down. So I'm going to try and share my screen now, and hopefully this will work. and you can talk us through how Planet Patrol works. Here we go. Let's try this. Okay, here we have Planet Patrol.
Oh, my mic was off, sorry.
Right.
So this vetting process that you mentioned, it has two main components and a few other minor components. The two main components, one of them is ruling out the sources that we discussed, like eclipsing binaries and instrumental noise, in the light curves themselves. Light curve is the brightness of the star is a function of time. It's basically, it's a curve on the screen of light, in a way. So this is half of the vetting process. About half of the vetting process goes into that. We look for features that may indicate an eclipsing binary. The other main component of the vetting process is not looking at these light curves, but instead at the images, at what the spacecraft is actually seeing, what the instrument is actually measuring, even before creating the light curves. These light curves are created from these images. Mm-hmm. And we use these images to figure out which part of the image is changing during the transits that we detect. As Simon mentioned, what the instrument sees is pixels. It sees these squares, 10 by 10 or 15 by 15 squares, centered around on the target, and it measures the brightness of all the pixels on this image, all the little individual squares on this image. Ideally, what we want to see is a uniform dark image and a single bright spot around the position of the target. This would indicate that the target star itself is indeed changing in brightness during the detected transits. This is in the ideal world, this is the spherical cow in a spherical problem in physics, which unfortunately, because of many different noise contributions, many of the images don't look nice and clean. There are different artifacts, and you can probably go through some of them. To do that, I think you need to go all the way to the top of the page, Simon, and okay. And click on classify.
Okay.
So we basically show every image for every transit for every planet candidate detected by TESS. Each of these images will show how the star looks like during that particular time, during the time of each transit. This is a good start. This is a messy image.
Okay.
This is nowhere near what we want to see.
Looks like a nice planet.
Yeah, unfortunately not.
So explain what we're seeing here, because there's lots of things going on. We've got the rectangle here, and we got a dot here. It's pretty much blue throughout, which suggests there's uniform intensity, and white is a higher intensity. It's a color map, like sort of weather map you see on.
Yes. Yeah, it is a color map. Yeah. So what you see here is every pixel on the detector which is changing during that particular transit. Ideally, we want to see one or just a few concentrated pixels in the center of the image, where this dashed contour is. The dashed contour indicates the position of the target star. Okay. Now, TESS pixels are 20 arc seconds on a side. So in each of these pixels, there can be many, many different stars. It's not just the target itself, many different stars of different brightnesses. So this is actually what's called a difference image. We basically monitor how the image changes during the times of the transits.
Right. So this is a reflection of extent of change over time rather than
exactly
brightness. Okay. Yeah.
Exactly. So if everything worked perfectly, we would have seen a single bright spot, basically inside the dashed contour.
Okay.
In this case, what we see is a complete mess.
This is a mess. We want to ignore this. And of course, this is real science here. It's nice when you see all these beautiful Hubble images, but when you get down into the weeds, these images don't necessarily look beautiful.
Exactly.
But begin to look more beautiful the more you understand what you're looking at. So what's the best thing to do now? If I click continue?
So actually, this is the tutorial. So you can probably actually close this.
Okay.
There's it, yeah. And so this is the actual classification where we basically ask people, does the image that you see look like a uniform dark background with a single bright spot somewhere in the center of the image? Mm-hmm. If it does, then they click yes, and this the response is recorded in a data file so that later we can use. Okay. If it is not, like in the mess that we see here, we give 3 different options which will help us improve the analysis and also improve the algorithms that are used to produce this image. Mm-hmm. So in this case, it's basically noise, that there is nothing that stands out in the image with respect to the background. Okay. And let's ignore the red dot for the moment. The red dot in this is not a good measurement anyway. So poor image.
Poorly defined spot, would this be a
poorly defined spot?
Yeah. Okay, let's pick that one. And of course, it gives you some help files as well, because like any sort of image recognition, you have to get used to what you're looking at, don't you?
Yeah, exactly.
Then it becomes the human brain. It's a computer that's been in production for 2 million years, and so it has an incredible pattern recognition system. But it needs to recognize, what it's looking at first before it can make those decisions. So I'm going to hit done here. Okay, this looks a bit better.
It does. It is not fantastic, but overall there is a dark background. Overall, there are a couple of bright pixels clustered together inside where the target should be. Mm-hmm. And now, so the red dot actually measures the position of the image, the position of the brightest part of that image. Mm-hmm. So now the red dot allows us to go with a sub-pixel precision. So you don't just say, oh, so pixel 5 is the brightest. No, we actually go inside that pixel now. And we want to do that because these pixels are very large. They're 20 arc seconds away on the side. There can be many stars within these 20 arc seconds. So we want to get as close to the target star as possible, given the data at hand.
Okay. So this one, what would you be happy with this? If I saw this, I'm saying, oh, I'm getting there.
I'm perfectly happy. It doesn't look great, but from experience, this is in many cases as good as it's gonna get.
Okay. So we're going to say yes here because we're optimistic that we've discovered the second Earth.
Oh, and by the way, before you do that, there's a little eye under the image. Do you see that?
Yeah.
So if you click on that, so now this should tell you the target. What are the coordinates of the target on the sky, the right ascension and declination. It gives you the tick ID. This gives you the number in the TESS catalog of stars. Mm-hmm. It gives you a link that tells you a lot about the target. But before we go to that link, just from the name of the image, what you can figure out is the first number is the tick ID. This is the ID of the target. Mm-hmm. The second number, this is the period of the detected transit. So in this case, this is a 2.07 days period of an exoplanet candidate. Mm-hmm. The next number gives you which sector in TESS this was observed in. TESS is observing 13 sectors per hemisphere, and so on and so forth. So it gives you a lot of information about that star. Mm-hmm. And if you click on the link now, okay, it will send you to the ExoFOP page, ExoFOP TESS page. So this is a page dedicated for the properties, and also it enables the analysis of all the planet candidates, or the vast majority of planet candidates discovered from TESS. Mm. This is a very busy page, but here you can find a lot of information about additional information about the star itself. And if you go down, actually, no, you don't even need to go down. There is a table that says planet parameters. So mm-hmm. Here you can actually see what are the parameters of the planet candidate that you're seeing. The period, the depth of the transits, and so on and so forth.
That's wonderful. I'm going to stop sharing now because I think if people want to know more, they can dive into the site, which will be amazing. So we've had a few more people signing in, and we've got a few questions coming up here from the audience. So I'm going to change tack now. First of all, how long has Planet Patrol been up and running?
What is today? Wednesday, so 8 days.
8 days, okay. And how many images have been analyzed by citizen scientists in 8 days?
About 400,000 now.
400,000.
Yeah.
So this has become quite a popular pastime for citizen scientists to do that analysis. And that, of course, once those are done, as we just did that sort of test run, the candidates that look promising are then fed back to the scientists themselves for confirmation. Yes. Is that how it works? Okay.
Absolutely, yeah.
Wonderful.
And just to give you an idea, and actually this goes back to your question, why Planet Patrol? So, well, we have about 4,000 citizen scientists looking at the images. Our group is 4 people. So it took them 1 week to do that. We're 1,000 times smaller group, so it would have taken us 8,000 weeks to do this.
Okay. And hence the great benefit of bringing in some casual help to do this. That's wonderful. I'm going to turn now to some of the questions here, and some of these maybe we can talk about TESS and then talk about more general. First question is, what's the furthest exoplanet that's been discovered so far in terms of distance, I suppose? What about TESS and what about EVA?
Oh.
Do you have those numbers on the top of your head? There's a good test.
I don't, and these numbers constantly change because we keep, detecting planets. But I would say the next galaxy over. Probably, if you Google the most distant planet, it will come up with a planet, probably in another galaxy, probably in M31. But well, it's not a planet. It's always a planet candidate, right?
And
so,
for TESS, of course, we're only looking at the brightest nearest stars. I think some of these very, very high distance exoplanets are discovered by what's called gravitational microlensing.
Yes.
And so that is a very, very different technique. And we should do a SETI Live on gravitational lensing, because that's a pretty cool topic. But TESS, of course, are much closer. What's the typical distance of a TESS star, roughly?
Good question. I don't know about the typical distance, but I would say that the stars that are most interesting are the closest ones. So ballpark, I would say 100 parsecs, which is about 330 light years.
Right.
Is a good. It's a decent rule of thumb of the population of planets that we get from TESS.
Right. So
and it's a broad distribution. So you go from a couple of parsecs to hundreds of parsecs, but most of them would be within, I think, 100.
Okay, so a few tens of light years to 100 light years. So close in astronomical senses, but not that close should you want to launch a spacecraft, or should aliens want to launch a spacecraft to visit us. It's still a bit of a distance, isn't it?
Yeah. I mean, you can launch, but you have to wait a really long time to get there.
Another question, does TESS have a spectrometer? Or is it?
No, unfortunately, no, it's a pure photometer.
Okay. And that means, of course, that any observations to look at more detail would have to be done, presumably by larger ground-based telescopes, which is where you would pass that data over to.
Absolutely. TESS is the kind of detection vehicle, and then the characterization vehicle, you need something else, like Hubble or hopefully James Webb and others. But TESS is only the detection vehicle. Of course, we do characterizing, but it's only based on the photometry.
Another question, are any of these systems close enough where it'd be practical to look at the details of the planets? And I think that, just following up from that last question, to actually start looking at the information about the planets themselves, which is not difficult, not easy, rather. The planets are very, very small and, far away. We're now talking probably about the next generation of space telescopes, aren't we? Do we even get details from these?
Yes, for most of the planets, yes. And it depends on the type of planet. Large planets will have a stronger signal. Small planets will have a weak signal. But there has already been a lot of good results coming from Hubble, from spectroscopy from the Hubble Space Telescope, and a few actually observations from even from the ground. I'm talking only about spectroscopy. And of course, this is the holy grail. We want to get, down to the size of Earth, ideally, and try to detect. First thing, try to even detect an atmosphere around such a planet, and only then, decide to dig even deeper.
Right.
But spectroscopy, which is what is called a transmission spectroscopy, meaning that you try to detect the atmosphere of the planet as it crosses the disk of the star, is already being done with Hubble.
That's
Mostly on large planets, of course, mostly on large planets, because the signal is tiny. The signal is tiny. The noise is huge, so it's not an easy task.
Yeah. Another question: Who names exoplanets? It's not something we can sell to the audience here to make money. It's,
yeah.
How is the decision? And not many of them have been named, have they yet? What's the naming convention at the moment for an exoplanet? Once this citizen scientist passes back this information, it's confirmed as a planet. What's the naming convention for exoplanets?
So the typical convention is, well, we're already looking at stars with no names. So usually the way that we do things is we basically add a letter to the designation of the star. So for example, if you look in the sun, Earth will be Sol-B, A, B, C, D, Sol-D, because it's the fourth planet from the sun. So
yeah. So really, you take at the moment you're taking the star's name, which, as you say, these stars are only in very obscure catalogs and don't have names, and the star itself is the number, what it is, 1054.
Yes, exactly.
And then the planet will be 1054b for the first one discovered,
Exactly.
B for the next one discovered, and so on.
Exactly.
It's going to be a long time before we actually start naming these. I've got a feeling.
Yeah. And some of the stars have names. Many of the stars have actual names instead of catalog numbers, and we already discovered planets around the named stars.
Mm-hmm.
So.
Just a question again about being a citizen scientist. What sort of feedback will, if I went back into this now and started playing around and got this candidate that turns out into a planet, what sort of feedback would I get? With how much information would I get for that helping that discovery?
Yeah, so that's a great point. So we have what we call like an advanced users group, which means that anyone who is interested in participating further in this process, participating further into this vetting process, can join our group, and we do regular meetings. And ideally, down the road, we analyze the data and we publish the data. So anyone who is interested in participating in this, working in these results, and getting, officially recognized as a co-author on a paper, this is part of the process. So anyone can reach out to us and express interest. And at the end of the day, most of the papers who have citizen science contribution does acknowledge this, either in the authors or in the acknowledgements themselves.
Right. So you can, by doing this, yes, you're not a professional astronomer, but you can get recognition. You can get your name on a scientific publication, which is
absolutely.
Yeah.
And this is already the standard. People do this. Yeah.
Wonderful. So I think we're running short of time here. Just one last question. What next? What next for you? What next for TESS? What next for Planet Patrol? How are things going?
So one by one, next for me, a lot of work analyzing the data. For TESS, hopefully more planets on long orbits. We're all rooting for that. For Planet Patrol, we plan to add a second, what's called the workflow, a second part of Planet Patrol, which will be vetting not the images that I mentioned, but the light curves themselves. So the second part of this vetting process, where people can actually go through the light curves and see features in the light curves.
Thank you, Veselin, very much for the conversation and Planet Patrol. And as we said, go to the SETI Institute webpage to find out more about this. SETI Live is a weekly program, varies in time, but we try and do weekly discussions with our scientists and other scientists who are doing fascinating work. This is a free presentation. If you're interested in supporting or getting involved in the SETI Institute anymore, then please do sign up for a newsletter. There is a nice bright red donate button at the top of the page. We will continue doing these SETI Lives. What we're also got coming up is on the 22nd of October is our SETI Talks. These are much larger, grander events that are an hour or so long with lots of panelists, and there's going to be one on the 22nd of October. That's going to be daytime for Pacific people, but again, check our website. Later on, we'll have much more information on that. So good luck patrolling those planets and making more exoplanet discoveries. Very, very exciting.
Thank you, and thanks so much for the interest and for having me here.
Take care, and bye-bye, everyone. Thanks for listening.
Bye-bye.